Hey everyone, welcome to The Explainer. I am so thrilled to have you here today. Look, if you've ever played around with a modern large language model and found yourself wondering, wait, how exactly does this machine actually understand what I'm saying? Well, you are definitely in the right place. Today, our goal is to completely demystify the core architecture that is literally powering the AI revolution right now. The transformer. We're going to break down exactly how this incredible tech processes language. And spoiler alert, it's not just a boring static dictionary of words. It's more like a living, breathing web of context. Okay, let's dive right into this. All right, so here's our cognitive map for today's journey. We'll start with the problem with context, take a peek inside the transformer block, explore the magic of attention, break down queries, keys, and values, and finally wrap the whole thing up with multi-head attention. Let's get going. So starting off with section 1, the problem with context. Simply put, human language is messy, right? Words almost never mean just one thing in isolation. Think about these two sentences for a second. The chicken didn't cross the road because it was too tired. And the chicken didn't cross the road because it was too wide. As humans, we instantly know that in the first sentence, the word it refers to the chicken, right? Because chickens get tired. But in that second sentence, it clearly refers to the road because roads are wide. But here's the catch. For older, static embedding models, the word it is represented by just a single, fixed string of numbers. It's mathematically identical in both of those sentences. So this presents a pretty massive mystery. If a computer is reading left to right, processing text sequentially, how on earth does it figure out if it is the feathered bird or the asphalt street? I mean, when it hits the word it hasn't even seen the words tired or wide yet. Well, the solution isn't to just give the computer a static dictionary definition. The actual solution is something called contextual embeddings. Instead of locking in a fixed meaning, the transformer builds these dynamic, incredibly rich representations of a word's meaning by actively looking at and integrating information from the surrounding words. The word it basically becomes a sponge. It soaks up the context of chicken and road and whatever comes next, adapting its mathematical meaning completely on the fly. Moving on to section 2, inside the transformer block, let's actually look at the residual stream to understand exactly how these contextual embeddings are forged. Imagine you're following a single word, we'll call it a token, as it travels up through the network. Notice that vertical gray bar. That is the residual stream. You can kind of think of it like a main highway. The token's initial embedding starts at the bottom and travels straight up this highway toward the output. But along the way, it gets continuously enriched. Information is pulled off the highway, processed through the multi-head attention layer and the feed-forward layer, and then boom, that new enriched context is added right back into the residual stream. It's just a continuous process of constantly upgrading the word's meaning. And here's the bigger picture. We don't just do this for one single word. Stacked transformer blocks process an entire context window all at once. Check out how the arrows weave across the columns here, processing the phrase "so long and thanks for." Information from preceding words is constantly flowing into the current words column. So layer by layer, block by block, these contextual representations get richer and richer until they finally hit the language modeling head at the very top. And that head uses all that beautifully built-up context to predict the most likely next word, like, say, all. All right, section 3, the magic of attention. This right here is the true superpower. This is what separates transformers from basic old-school neural networks. Self-attention is precisely how we solve our chicken and road problem. It's essentially a mechanism that allows the model, when it's processing the current token, to look back at all the appropriate prior tokens, figure out which ones are actually relevant, and then combine their representations into the current token's residual stream. And this visual brilliantly illustrates that exact concept in action. We're at layer K+1, trying to process the word it. See those blue highlights reaching down to the previous layer, layer K? Notice how the lines connecting to chicken and road are bold and really heavily shaded blue. That right there is the self-attention distribution. The model is mathematically assigning a really high weight to chicken and road while pretty much ignoring filler words like the or didn't. It has learned that to understand it literally has to draw heavily on the nouns that preceded it. This is exactly how that contextual meaning is built. Now, if you want the simplified mathematical intuition for how it assigns those blue weights, it basically all comes down to similarity. The model takes the mathematical vector of the current word and compares it to the vectors of all the previous words using a dot product. That dot product naturally gives a higher score to vectors that are similar or relevant to each other. The model then takes those scores, converts them into a set of probability weights, and uses them to sum up the values of the previous words. Which brings us to section 4, queries, keys, and values. Because, of course, it's slightly more complex than just a basic dot product. Let's peel back that simplification and introduce the specialized roles that actually make this all work. Think of self-attention almost like a highly organized networking event. Every single token in the sequence gets projected into 3 distinct roles using weight matrices. First step is the query. This is the current token basically asking for context. So when our model is processing the word it is holding the query. Second are the keys. These are the preceding tokens offering up their answers or labels. In our example, the words chicken and road are holding up their keys. And third is the value. This is the actual substance, the underlying meaning of the preceding token that's going to get extracted and summed up to enrich our current token. So the really crucial point here is how these 3 roles interact in a 5-step recipe. Step 1, every token is projected into its query, key, and value representations. Step 2, the current token's query is compared against every preceding token's key using a dot product. And if the key matches the query, the score goes up. Step 3, just to keep the math stable and avoid messy gradient issues, we scale that score down by dividing by the square root of the dimension. Step 4, we apply a softmax function. This takes those raw scores and turns them into clean, easy probability weights that sum to exactly 100%. And finally, step 5, we use those percentage weights to multiply and sum up the value vectors of those preceding tokens. We can actually see this exact recipe mapped out structurally here. Look at how the third input, x3, operates. First, it generates its query key and value. Then its query reaches back and compares itself to the keys of x1, x2, and even x3 itself. These comparisons generate those attention weights, which then act like a filter, deciding exactly how much of the values from x1, x2, and x3 get combined to produce the final output for that attention layer, which is A3. Now, there's a really fascinating architectural secret to all of this, and it involves the number 512. In the original transformer design, after all this complex query, key, and value multiplication is completely done, the final output matrix is multiplied by one last matrix to reshape it back to exactly 512 dimensions. But why? Well, because the input to the block was 512 dimensions. By making sure the output perfectly matches the input size, these transformer blocks become incredibly modular. You can literally stack them on top of each other infinitely, just like Legos, passing that residual stream smoothly through dozens or even hundreds of layers. All right, on to our final section, section 5, multi-head attention. Because as brilliant as one single attention calculation is, human language is just way too complex for a single pass. Think about it. If you only have one attention mechanism, it might spend absolutely all its effort just figuring out our chicken and road pronoun problem. But what about the grammar? What if a subject needs to agree with a plural verb? Or what if a word has multiple meanings, like the word bank next to a river? To handle all of this at once, the transformer uses multiple parallel attention heads simultaneously. Each head gets its own independent set of query, key, and value matrices. That means head 1 can focus entirely on figuring out what it refers to, head 2 can focus on grammatical subject-verb agreement, head 3 can look at spatial relationships. They all do their specialized jobs in parallel, and then their outputs are just concatenated, squished back together, and passed on up the chain. And that brings us to the ultimate question. We've just walked through how a single token uses multi-head attention across a few layers to dynamically understand the context of a tired chicken and a wide road. But modern large language models, they don't just use one block or a few heads. They use hundreds of layers, with dozens of heads scaling up to literally hundreds of billions of parameters, all acting in parallel on immense, massive windows of text. If this elegant, beautifully targeted math is what happens at the microscopic level of just a single word, just imagine the staggering, emergent comprehension that becomes possible when you scale this architecture to the size of the entire internet. It really makes you wonder, what can't they learn to understand? Well, thank you so much for exploring this with me today. Keep learning, keep questioning, and I will see you in the next explainer.